Hello everyone. We are glad to introduce our paper, Decompose More and Aggregate Better. 2 closer looks at frequency representation learning for human motion prediction. Our team members are from Xi'an Jiaotong University and Tencent AI Lab. Sincerely, you can scan the QR code at the top of the screen for more details of the paper. Human motion prediction focus on developing a powerful predictor F-pred that infers future body movements from historical poses. Recently, frequency-based representation learning verifies its effectiveness in encoding temporal dynamics. And many works tend to conduct frequency representation learning after discrete cosine transform, DCT. Taking 2 methods as examples, their proposed predictors F-pred can be uniformly factorized into 3 stages. Given a human motion history X, function DCT first converts it into the frequency space. Then, function ENC extracts its frequency-based motion representation. Finally, function IDCT converts it back to the pose space for motion prediction. In this paper, we reformulate the frequency representation learning into a novel decomposition aggregation scheme. And we briefly compare the strategy difference via a paradigm review. Please scan the QR code at the top for more details. First, we would like to briefly introduce the background and applications of the human motion prediction task. Human motion prediction systems focus on developing a powerful predictor F-pred that effectively infers future 3D body movements from its histories. These predictive methods are fundamental to many real-world applications, including sports analysis, autonomous driving, and human-machine interaction systems. Then, we briefly sketch previous human motion prediction works and summarize their modeling strategies. Here, we take 2 methods as examples and find that their proposed predictors F-pred can be uniformly factorized into 3 sub-stages. Specifically, given a human motion history input X, function DCT first converts it from the initial pose space into the frequency space with discrete cosine transform. Then, function ENC extracts its frequency-based motion representation. Finally, function IDCT converts the extracted frequency-based motion representation back to the pose space for motion prediction. As a common used strategy, frequency-based representation learning verifies its effectiveness in encoding temporal dynamics. In contrast to the initial 3D pose space, frequency space encourages human motion systems to focus on trajectory-related cues, significantly improving its robustness against body shape perturbation and coordinate system shift. In this context, the frequency features extracted from past body motions dominate future motion prediction. However, there still remain underlying challenges for powerful frequency representation learning. One challenge is the intra-sample difference. Since the human skeleton is a non-rigid articulated structure, different body joints exhibit different frequency appearances in their motion trajectories. The other challenge is the inter-sample difference. Different personal motion styles in the same activity bring subtle intra-class bias to different data samples, enlarging the frequency representation gap between human motion samples. In these cases, a further investigation into developing a powerful frequency representation learning framework for robust human motion prediction remains fundamental yet underexplored. In this paper, we propose to develop multi-view augmentation learning into a promising solution for robust human motion prediction. Specifically, instead of extracting features from a single frequency space initialized by the DCT, we first introduce an input body motion into multiple frequency spaces to enrich its spectral encoding. Then, we collect richer multi-view frequency representations from these spaces for robust human motion prediction. As illustrated in the above figure, firstly, frequency decomposition unit unweaves finer frequency representations from an input body motion by tuning each body joint trajectory with multiple versatile filters. Then, Feature aggregation unit deploys a series of adaptive graph filters within each frequency space and interleaves feature crossing layers to promote message exchange between spaces. Finally, we briefly compare the strategy-wise difference between our method and others via a paradigm review. Following the standard evaluation metric commonly used in previous methods, we adopt mean per joint position error, that is MPJPE, as a metric for quantitatively evaluating 3D human motion prediction. The above table shows the MPJPE performance comparison between our method and others on the human 3.6M dataset. These short-term and long-term prediction performances verify the effectiveness of factorizing the frequency representation learning into the proposed decomposition aggregation scheme. Furthermore, as shown in the bottom left figure, our method significantly outperforms these baseline methods when training with 10%, 30%, 50% data samples. It indicates that the multi-view frequency representation augmentation enriches the spectral diversity of body motions and prevents the prediction system from overfitting on limited training samples. Besides, as shown in the bottom right figure, we also analyze our prediction accuracy improvements on each body joint. Here, we briefly summarize the core contributions proposed in the paper. Many thanks for your watching. We look forward to you scanning the QR code at the top of the screen for more paper details.